Hi guys, I'm Suraj from Sri Venkateswara College of Engineering. Today we are going to see about a topic which comes under design and analysis of algorithms, which has a subject code 21CS42. The topics that are to be covered in this presentation are knowing about what is an algorithm, then we'll come to the Huffman tree, and then we'll come to how to design the Huffman tree algorithm, and at last we'll derive the analysis of different case efficiencies, that is best case, average case and the worst case. First, coming to what is an algorithm. So it is a set of commands that must be followed for a computer to perform calculations or other problem solving operations. An algorithm can also be said as a finite set of instructions that are carried out to perform a specific task or a specific order. Now, what is this algorithm actually? It consists of a problem. The problem can be defined as a real world problem or real world instance problem for which we need to develop a program or a set of instructions. The algorithm is a step-by-step process that will be designed for a problem. It consists of input. After designing an algorithm, it is given the necessary and desired inputs. The inputs are passed on to the processing unit. The processing unit then produces the desired output. The output is the final result of the program. Now, coming to what is an Huffman tree. The main concept behind this Huffman tree is it uses a greedy algorithm to build a prefix tree that optimizes the encoding scheme so that most frequently used symbols have the shortest encoding path. Huffman coding is a technique of compressing data to reduce its size without losing any of the details or the data present in it. It is generally useful to compress the data in which there are frequently occurring characters. Now, coming to designing of the Huffman tree. We'll first know about the algorithm. So in this Huffman tree, we first create a priority queue. Capital Q consisting of each unique characters. Then we sort them in ascending order of their frequency, according to their frequencies. For all unique characters, we create a new node, then we extract the minimum value from the priority queue and we assign it to the left child of the node which is created newly. Then we extract the minimum value from priority queue and assign it to the right child of the new node. Then we calculate the sum of these two minimum values and assign it to the value of the new node. Then we insert this new node into the tree and the tree will be returned as an output. Now, let us understand the Huffman tree with the following example. Consider an example where there are characters which have the corresponding frequencies. The characters are A, B, C, D, E and F, which has the frequencies 5, 9, 12, 13, 16 and 45 respectively. Now what we do is we build a min heap that contains 6 nodes where each node represents root of a tree with single node. Here there are 6 characters and 6 frequencies. So first we take the sum of the least two numbers, that is 5 and 9. So 5 plus 9, here 5 plus 9, which gives us 14 as the value. Then it is assigned to the left child as well as the right child. The left child has A5, which is here, and B9, which gives 14 as the result. So now the heap contains 5 nodes where 4 nodes are the roots of the tree with single element each, and the heap node is root of the tree with 3 elements. Now the internal node is 14 as it is shown in the previous slide. We extract two minimum frequency nodes from this heap and add a new internal node with frequencies, that is 12 plus 13, which is 25. The left child has C12 value and the right child has D13 value as shown here. Now the min heap contains only 4 nodes and where 2 nodes are the root of the trees, that is 30 and 14, with single element each, and two heap nodes are root of the tree with more than one node. So in this what we do is, we extract two minimum frequencies from the heap, that is 14 and 16, and we create a new internal node with frequencies 30, which is a new element, 14 plus 16, which give rise to 30. Now, now the min heap contains only three nodes, 25, 30 and 45. Here also we do the same thing. We extract two minimum frequency nodes, then add it to a new internal node, that is with frequency 55, that is 25 and 30, which give rise to 55. Now 25 has the left child as C12 and right child as D13. 14 has the left child as A5 and right child B9. 30 has the left child as 14 and right child as E16. Now this gives rise to the 55, which is the main node of the tree. Now the min heap contains only two nodes, that is 45 and 55. As there is no other choice, we take these two as the smallest minimum frequencies and we add them, 45 plus 55, which gives rise to 100. Now it becomes extremely easy for us to encode the code words for the following characters. For the character F here, we start from the main node or the root node and traverse to the element F. While traversing, the code word that comes on the path are added onto the table. So to go to element F, there comes only one code word in the path, so 0 is added to the table. Next, coming to the element C. To traverse to the character C, we again start from the main node, then we follow the smallest path that takes us to the element. While traversing, we get 1. So first 1 is added to the table. Then 0 comes in the path. So 0 is added to the table. Then comes 0 again. So again 0 is added. So the code word for C will be 1, 0, 0. Next element is D. To traverse to the D, we again start from the main element. We traverse to 55 and we get the code word as 1. So 1 is added onto the table. Then we come to the left, which comes with the code word 0 on the path. So 0 is added onto the table. Then comes 1. So 1 is added onto the table. So code word for D will be 101. Next, coming to A element. For A element which is present here, we again start from the main node and we traverse until we reach A element. So while traversing, we get 1 as a code word first. So 1 is added onto the table. Then again comes 1. 1 again is added onto the table. So likewise, we traverse till we get A and the same code words are added onto the table again and again. Likewise, A will get 1100. Likewise, B will also get 1101. And last, E will get as 111. Now, we will see the different time complexities of the Huffman tree. They are best case, average case and the worst case. First starting with the best case, the time complexity for encoding each unique character based on its frequency is 0 into n log n. Extracting the minimum frequency from the priority queue takes place 2 into n minus 1 times and its complexity is 0 into log n. Thus, the overall complexity by adding 0 into n log n into 0 into log n will give us 0 into n log n. Next, coming to the average case. The average case efficiency of Huffman code is therefore equal to 2.14 divided by 2.2. The Huffman algorithm is optimal in sense that it generates the shortest possible average code word length for a certain source. Next, coming to the worst case. The worst case of Huffman tree can happen when the probability of a symbol exceeds 2 minus 1, that is 0.5, making the upper limit of inefficiency unbounded. Thank you everyone for giving your precious time by listening this problem presentation and hope you understood all the concepts that are covered in this presentation. Hope you enjoyed learning. Thank you.